is our first lesson on the waves topic, which deals with oscillations. And what I mean by an oscillation is a particle which moves around a fixed point back and forth. And it can move in any plane, so it doesn't need to just go back and forth. It can go forwards or backwards, up and down, at any angle to it. But essentially it's all moving about a fixed point, so it comes back to the fixed point, to the other side, back to a fixed point again. And this is really useful in physics because there are hundreds of particles and conditions in the world which you can model using this idea of a single particle moving back and forth and then saying many particles do it. And it actually comes out to predict lots of really interesting things in physics. However, some particles move faster than others, and some particles move in different directions, so you need a way in physics to describe one oscillation from another. And that is what hopefully this video will teach you. So let's think of a more concrete example. Let's think of a mass on a spring, and here is our spring. And as you pull it down, so the spring becomes stretched, and when you release it again, of course, the spring will cause the mass to go back up again, and you'll get this movement up and down between a high point and a low point, a high point and a low point. It's identical to what we've got in this instance. We're just rotating it up and down, and you'll be doing an experiment on this as well. Now, what's important first of all is to say, well, what's one complete oscillation? Because it can do this hundreds, thousands, even millions of times. So we will need to work out what's one complete oscillation. Well, whether it's side to side or up and down, one complete oscillation is from the start point, it goes up to its extreme in the other direction, whether that's up or to the side, and then back down again to its start point. And that is one oscillation. Now, it doesn't need to be from the bottom or from one side, it could be from the other side potentially. And it moves, or in this case up, it moves all the way to its bottom point and then back up again to where it started. So in this case, this is our start point. Or interestingly, we could have it from where it is at rest, in the middle, and it could go up to one point, down to the other point, and back round where it started from. And all of these represent one oscillation. And that is really useful because when we look at any oscillation that takes place, we will always reference it to what it's doing for just one of those, and then scale it up to let it do 1,000, million, hundreds, or even halves, millionths, thousandths. But you must understand what an oscillation is, first of all. So one way to describe one oscillation from another is to look at how long it takes for one oscillation to occur. And that idea is called the time period. And this is the first concept I'd like you to memorize. So the time period is the time it takes to complete one oscillation. And we always reference that in seconds. So the time it takes in seconds to complete one oscillation, which is the time period. And we often give it the symbol T. Now let's just try a few examples. Because quite often these vibrations might be very, very fast, so therefore you won't have a chance to time just one oscillation. You might only have a chance to time, say, 10 oscillations. So therefore, let's look at what happens if you measure more than one vibration, and let's work out how much the time period will be. Okay, let's imagine we have, here's the first example. Let's imagine we have 10 oscillations in 5 seconds. Okay, what's the time period, do you think, of that oscillating body? You think you know, hit pause and work it out. And here comes the solution. So essentially what we're saying is, if we've got 10 oscillations in 5 seconds, we're wanting to work out the number of oscillations in 1 second. So we take the total time and divide it by the number of oscillations. So I'll just put that in brackets. So the total time and divide it by the number, hashtag oscillations. And in this case, that gives us 5 over 10, which gives us a half. Now try not to leave things as halves. Try to leave things as decimals. Physics prefers decimals because they're measurable. 0.5 of a second for this example. That is the time period. Okay, let's try another example. What about if we have 100 oscillations in 20 seconds? Okay, what's the time period going to be? If you think you know, hit pause and work it out. Otherwise, here comes the solution. Okay then, so we're looking for our total time, which is 20 seconds, and we're divided by the number of oscillations, which is 100. And that comes out with a nice fraction of a fifth, but we want to leave things as decimals, so 0.2 of a second. This is getting really quite fast now. So in a fifth of a second, 0.2, it's managed to do from the start point to the finish point. Excellent. Okay, and then finally, maybe a little thing to catch you out here. What happens if we had 6 oscillations in 1 minute? What's the time period? If you think you know, hit pause, but otherwise, here comes the answer. Okay, once again, the total time is 1 minute, but of course 1 minute we need to convert into seconds because time period is always measured in seconds. And then we need to divide by the number of oscillations, which is 6. And that brings us out with 10 seconds is the time period. Perfect. Let's move that to one side for a minute, and let's talk now about another measure of oscillations, which is rather than talking about the number of oscillations per second, now we're going to talk about, rather than talking about the time for one thing, we're going to talk about the number of oscillations per second. And this is going to give rise to this idea called frequency, given the term F. It's measured in hertz, which is given the symbol Hz. So the frequency are the number of oscillations per second, and you measure it in hertz, which is Hz. Okay, let's just think about that now. We're working towards an equation that links the time period and the frequency, but let's just think about some examples first when we do this. I'm going to try and show it graphically. Let's imagine that one oscillation, so here comes, let's draw this here. One oscillation takes 0.5 of a second. In other words, what we're saying is the time period is 0.5 of a second. Let's think about that. Here is one oscillation, point to point, and it's 0.5 per second. So in essence, what you're asking is the number of oscillations per second is a frequency. So what do you think the frequency would be here? If, of course, this were 1 second. Well, in actual fact, you'd be able to fit 2 oscillations into the 1 second gap. So what we'd say is that there would be 2 oscillations in 1 second. Or, if you like, we can say that that gives us a frequency of 2 hertz. Right, let's think of 2 more examples. How about one oscillation takes us 0.2 of a second, or time period is 0.2 of a second. Okay, let's think about that timing now. Now we have one oscillation is 0.2 of a second long. So now what we're asking for again is how many will fit into 1 second? Well, hopefully, with a little bit of maths, you can work out that there are 5 0.2s that fit into 1 second. Add those up. That gives us 5 oscillations. Or the frequency is 5 Hertz. Okay, let's imagine another one here. Let's imagine one oscillation takes 2 seconds, or the time period is 2 seconds. Now this is quite interesting because though our 1 second is there, this complete wave takes 2 seconds. So how much is 1 second of this complete wave? Well, it's a half of it. So therefore it's half an oscillation. Or in other words, frequency is 0.5 Hertz. So hopefully you're able to see here what we're trying to say. We're making a reference point of 1 second, and we're saying how many waves can you fit into 1 second. Now let me just draw a table of those results. The time periods in seconds, and the frequency in Hertz. And initially we had a time period of 0.5, and the frequency was 2. The next example was 0.2, and the frequency was 5. The final one was 2, and the frequency was 0.5. Now I want you to try and work out if you can see a relationship between the two of these, and it might help if I were to write it as a fraction. This is the only time I write it as a fraction, otherwise we write everything else as decimals. Can you see now a relationship going on between these figures? Okay, now hopefully what you have seen is that these numbers replicate themselves. So therefore we can say the time period is 1 divided by the frequency. Or the frequency is 1 divided by the time period. Note here, the time period was a half. 1 divided by a half gives us 2. It's quite a tricky one there. However, the frequency here, the time period was 2, so 1 over 2 gives us a half. The frequency is a half. So hopefully you can understand where these relationships have come from, and you need to be able to memorize those two equations or rearrange just one of them. Remember, these items, these parts of the formula can exchange places quite happily. Okay, now with that in mind, let's look at a few more examples. Being able to bounce between time period and frequency, hopefully with confidence this time. So the first one says that one oscillation is 0.1 of a second, or the time period is 0.1 of a second. What is the frequency? Think you know? Hit pause. Otherwise, here comes the answer. Well, we know that it's 1 over the time period. Let me write down, well, I could actually write it in a triangle. So if you prefer, you can write it as a triangle. So what is frequency? Well, you cover up the F, and that leaves you with 1 over t. Then you substitute the numbers. 1 divided by 0.1, which gives us 10. And remember always to put the units on. Number 2, here's another example. The time period, or the time it takes one oscillation, is 20 seconds. What is the frequency? If you think you know, hit pause. Otherwise, here comes the answer. Okay, we know the equation is now, if you cover up, yeah, we've done it before, we covered up frequencies 1 over the time period, so therefore 1 divided by 20 gives us 0.05 Hertz. Plug it into your calculator if you don't believe me. It does work. Next one. 2 more. We have now a frequency of 100 Hertz. What is the time period? Think you know, hit pause. Otherwise, here comes the answer. Now we cover up T, which leaves us with 1 over F. So our equation is 1 over F. 1 over the 100, 0.01 of a second. Good, okay, and the last one. This time we have 50 oscillations in 2 seconds. I want to work out what the frequency is, and there's 2 parts to this. You have to work out one factor first before you work out the next. You think you know, hit pause. Otherwise, here comes the answer. Let's first work out the time period, because we're not actually, this is not the time period. This is the time for 50 oscillations to occur, so we need to do what we did before. So we work out the total time and divide it by the number of oscillations. 0.04 seconds. Then we say the frequency is 1 over the time period, which gives us 25 Hertz. Excellent. Right, well I hope that makes sense. And if you understood that thoroughly, then coming onto waves should be straightforward.